Another use for the second derivative is to help us to identify a point of inflection. Now, as we saw that with the first derivative, we could find a point of inflection may occur because the first derivative is 0, and we can test the gradients either side and see that the gradient stays the same. But there's another type of point of inflection. And that's where the first derivative won't be equal to naught, but the second derivative will, and there will be a change in concavity. So there are points like, if you look here at A, where you can see that there's a change in concavity in this graph. It's going from concave up, and then after A, it's concave down. However, the gradient has been drawn there at A, and that gradient is not horizontal, so the first derivative would not be 0 there. So if the only way we had of identifying points of inflection was that the first derivative had to be 0, then we would miss these. We would miss points like A. We certainly wouldn't miss B. B is another example of a point of inflection. We've got a change in being concave down to concave up. But if you look at the tangent drawn there at B, the tangent is horizontal, and we would be able to identify point B if we put our first derivative equal to 0. Not the case with point A. Just solving first derivative equal to 0 doesn't identify A for us. However, A is a point of inflection. The names are slightly different. We call point B a horizontal point of inflection, which makes sense. The tangent is horizontal there. Now, for that sort of point of inflection, the first derivative is equal to naught, and also the second derivative is equal to 0. With point A here, it's only the second derivative that's equal to 0. So generally, to identify points of inflection, we go straight to second derivative and we solve second derivative equal to naught. Now, because that will give us all of them. At B, the second derivative will be equal to naught, as well as the first derivative, and concavity will change. So that's fine. Second derivative equal to naught will give us B, but the one that we're most able to identify are the examples like A. Now, so there are two things for points of inflection. Two things. One, concavity must change. It's no good just having the point 2, which is second derivative is equal to 0. I can show you examples where the second derivative is equal to 0, and that happens on y equals x to the fourth. No, what am I doing? X to the fourth. Y equals x to the fourth is a very flat-based parabola, very flat-based here. It has a turning point at naught. First derivative is 4x cubed. Second derivative is 12x squared. If I solve second derivative equal to naught, I get that x is naught. Now, at x is equal to naught, we have second derivative equal to naught, but we don't have a point of inflection. This is not a point of inflection here. This is concave up the whole way. So, just showing second derivative equal to naught is not enough to identify a point of inflection. So, I say learn that you will only get a point of inflection if concavity changes. Has concavity changed here? Yes, definitely. Concave up, now concave down. At point B, from concave down to concave up. That is the most significant feature for a point of inflection. This, however, is the easiest way to find it. Where it will occur is to find an expression for the second derivative, put it equal to 0, you'll find your x value, and then you will be able to test whether the concavity has changed. The way you will do that is to set up a little table of values. So you've established where the second derivative is equal to 0, and just like we did for gradient, we will choose something just to the left-hand side, a bit less than a, an x value just bigger than a, and we will look to see the signs of the second derivative when we substitute that value in. And so if we've got that it was a positive, then it was 0, and then it was a negative, so it was going concave up, 0, concave down, then we've got a point of inflection happening from concave up to concave down. Okay, so what have we got? We've got, if the second derivative is less than 0, we know a curve is concave down. If the second derivative is greater than 0, it's concave up. But for a concavity to change at A, and if we've got the second derivative at A equaling 0 and concavity changes, if we've got both these things happening, if the first derivative is 0, then we've got this thing called a horizontal point of inflection. But if we had second derivative equal to 0, concavity changed, and only the first derivative wasn't equal 0, it's just simply called a point of inflection. Revising that, or just putting that as a summary into a little table. Second derivative greater than 0, first derivative also greater than 0, the gradients are positive, concave up. You can have second derivative greater than 0, concave up. However, if the first derivative is a negative, the gradient's a negative, you've got concave up, but it's going in this direction. And if the first derivative was equal to 0 at A, then we've got a minimum. And you can go through the second one. Second derivative is negative, so it's concave down, but it's increasing. This one is concave down and decreasing, and max. And as a point of inflection, we've got concavity changing, and these are horizontal points of inflection. I will stop the video there and do this example in the next video.